So we have Dr. Shu Wu representing the Colorado School of Mines, our chair there, to give us a talk on gas EOR modeling for tight oil reservoirs. Please, Dr. Wu.
Thanks. This is Shu Wu from Colorado School of Mines. I'm Energy Simulation Reservoir Modeling Chair. Good morning, good evening, good afternoon. So can you see my slides?
Yes, we can.
Okay, thanks. My topic really is modeling study of gas EOR processes in unconventional oil reservoirs. So my research area in Colorado School of Mines with my research group, energy modeling group, really focus on unconventional oil gas flow and simulation. One current topic, actually research project, we have two ongoing research projects to look at CO2 or natural gas injection EOR approach. Then also we worked on thermal hydrologic mechanical THM or thermal hydrologic chemical THMC processes. We also continue or improve our modeling tool on fracture modeling study, like EDFM and MINC approach, enhanced MINC approach. Also work on CO2 sequestration and geothermal simulation. In past few years, we spent a lot of effort to develop a better modeling tool for hydraulic fracture and simulation by considering thermal effect and also stress shadow effects. The challenges, I think in addition to scientific challenge and technical challenge, political stuff, current downturn of the oil industry really have some impact on research funding, on recruiting of best students or researchers. So this is really some challenges we are facing. The objective of this talk really is discuss gas EOR for tight oil reservoir. Currently, in the US, the only feasible EOR approach is gas EOR, but it's still not really well understood. Some important impact like geomechanical impact and thermal impact are not included in most modeling studies. So in this presentation, we will discuss a multiphysical model to look at gas EOR simulation tools, and also to look at include geomechanical effects, thermal effects, and phase behavior, and the thermal nanopore confinement and geomechanical effects, and also look at some application for design operation gas EOR field implementation. This is outline for my talk. So after introduction, we'll talk a little bit about the model and numerical approach and present some simulation application result, then a conclusion. So the most material we are going to discuss here are published in this 5 journal papers in past 2 years. So most work have been done by graduate students and my colleague in my research group. So here, this is some of our own literature review result in past few years. In the US, CO2 flooding is the #1 EOR approach, has been used in past few years, surpass thermal recovery application. So typically CO2 can recover 5 to 25% additional oil recovery. More than 90% of world CO2 project will carry out actually in the US. So CO2 flooding contribute about 5% of total oil production currently. It's a tendency, I think, is a little bit slowed down for CO2 application in EOR, EOR, because mainly reason is the limited resources, CO2, and also economic climate. We know currently we also work on a project in the West Texas project for gas injection. So really the results show the only approach, like EOR approach work for tight oil reservoir is gas injection, huff-n-puff. Another benefit has been discussed before by previous presenter. It's really CO2 flooding or CO2 EOR operation is the best intermediate CCUS solution. Actually, this is an important area for current or future, near future oil industry. So the physically, we have thermal, we have the thermal multiphase composition of transport and geomechanical really fully coupled. So the observation really is done on the pore small scale. Then the formulation we use for fluent transport is on REV concept scale. The application really for field studies is on the reservoir scale. So this is the formulation that we talk about in the model. We fully covered multiphase composition mass transport, then thermal energy conservation, and geomechanical on the bottom. We have derived and used this mean stress formulation in past 10 years. So we figure out how to calculate actually the full stress tensor based on the mean stress formulation. So for geomechanical coupling, we need additional correlations. Here, this is some of the correlation list. So the porosity and absolute permeability is correlated with effective stress. This must be given for particular application. And also, because of multiphase phenomena, right, geomechanical coupling changes the pore geometry of fracture aperture, so impact directly on capillary pressure, which is must be given. And also, recent study also shows relative permeability is function also affect stress. So here, at least one citation of one journal publication still under revision is going to be published soon on some of the formulation. Numerically, we are still using integral find a different approach, fully coupled multi-composition mass balance equation for each component, and also for thermal conservation equation and the geomechanical equation, which is in terms mean stress formulation. So fully coupled, solve simultaneously together using Newton-Raphson iteration. Then this is another part. The phase behavior calculation, the flushing calculation become a little bit complicated once you include thermal effect and also nanopore capillary pressure confinement effects. So we have here, this reference, this paper published last year to look at truly three-phase equilibrium calculation, use some machine learning approach also, make speed up. And also we have isothermal case, we have different model. For isothermal, it's a little bit different. We still use Penn-Robinson US approach. So here, this is some validation for phase equilibrium calculation. So compare with published data. and also calculate some examples for phase behavior. Here, this is really something we have to do for the composition and nonisothermal coupling model. All the parameters here, we listed parameters or variables must be calculated by the model. So here we have temperature. Look at look at the viscosity, right? It's depend on the pressure or temperature because geomechanical coupling and the thermal coupling, so they change all the time. So this correlation must be given some from empirical studies. So let's talk about first example as non-isothermal CO2 flooding example. Here, this is the geomechanical data on the top. Here we have some flow properties, and this is original composition of the reservoir flow system. Very simple. This is geometry of the plan view of the model. So we inject from the top cold CO2, not reservoir temperature CO2. Here is producer. Then you will see some difference. Here, this is because fully coupled geomechanical. So you will see the saturation change. If you don't have geomechanical coupling, you won't see the saturation, gas saturation like this. This is for CO2 saturation here. Then the temperature, look at the temperature on the right plot, right bottom plot. So the temperature near the injector, you see temperature is lower. Also in the producer, because the phase change, right? The reason we include the temperature impact, because CO2 flooding, CO2 phase behavior is different from most other gases, right? It's changing from gas phase, supercritical to liquid phase all the time in reservoir condition. We know the Joule-Thomson effect, right? It's thermal exchange associated. So even you inject, right, you hope it's isothermal system. It's not. So you will see the impact on injectivity. Here, really, it's a big deal for unconventional reservoir. Inject liquid normally is not okay, right? Because of low permeability. Why CO2 works? Because CO2 even in the supercritical or gas or liquid phase still has very low viscosity. We can inject CO2 into tight reservoirs. Here, look at the inject temperature. We try 20 degrees CO2 at the inject and 40 degrees C or 60 degrees. The injectivity, look at, increase by factor, let's say here, 2, 40 degrees C CO2, injectivity increased by factor 2. If 20 degree CO2 inject, injectivity increased by almost 3, right? Factor 3. The reason is the cold CO2, right? The geomechanical effect, then the permeability will increase near the injector. So this is the big deal. Instead of fracking, for water flooding, many unconventional reservoirs become fracking instead of water flooding. So that's why as water flooding normally is not recommended for tight oil reservoirs. Here we look at bottom hole pressure with or without fully coupled the THM impact. Here you ignore thermal and mechanical impact. The inject pressure for the same injection rate is very high. But if we with a real physical model consider thermal and mechanical effect, so the bottom hole pressure, injection pressure is relatively low. This is more, give us more benefits here. This is the recovery factor for this particular model. Without THM impact, you see the recovery factor is really lower than the fully coupled approach because here this is physical behind. So here this is gives some demonstration. Thermal mechanical impact for CO2 flooding may be important. So next is field application. This is really, we do some both modeling and lab work. Here we are going to only discuss on the modeling work part. Here, some of the work has been published in this paper this year. Chongqing is the largest oil field in China now. So this is some of the data shown here. The location is really northern part of China here, middle of the country. Permeability is really low. Then pressure gradient also relatively low. So we have to have hydraulic fractures. They use water flooding, still use water flooding, but it's not very efficient. The recovery factor much lower than 10%. So here, this is a formation profile. We're looking into it. So the permeability here is 0.38 millidarcy. The porosity is about 12%. The thickness is about 20 meters. Anyway, here this is the key here for injector and producer. For injector, you inject from bottom because they inject water so far. The production on the top uses vertical well. What you see here, this is the wells. This is the region we're looking into it. We want to look at it through some modeling and modeling laboratory study to answer the question if the gas huff-n-puff is possible, is feasible. So because gas huff-n-puff is the best approach currently in the US, not gas flooding, actually gas huff-n-puff. So this is a region for 3D model. This is outline of the 3D model region. One horizontal well here, one horizontal well associated. Here, this is for next detailed model, we call sector model. One horizontal producer associated 6 vertical injector. So this is the, okay. First, we have done a phase behavior calculation. So for the composition modeling study, then we have to go through. We have lab data. We have core actually history matching and some sensitive study. Look at how to prepare the inject gas composition, basically recipe for better result, and look at some operation conditions like injection pressure, injection period, how long to inject, or how long to soak the formation. So here, this is some of the result. First, we pick 8 component, pseudo component composition model here. This is some beginning of the work for PREA. Before the calculation, we do some calibration of the phase behavior. So compare with the laboratory data set up, just the phase behavior calculation. This is the pseudo component we used for the composition model study. The second model is really one horizontal producer, 6 vertical injector. So here, this is initial 3D model calibration, larger scale model calibration. This is before we use the data directly from provided by the oil field. You will do calculation. The oil production rate is not too bad, but the injection pressure is very poor, very high. Look at the observation data is here. So the better result is here. This is after we did some calibration to look at for natural fracture permeability and also a relative permeability curve. So then we have much better. Here it's still not very good, but the most part here is much better for oil production rate. The key here is injection pressure. It's matched at least observation data, reasonable. Otherwise, here the pressure, injection pressure, much higher than braking pressure, not physically reasonable. So, composition effect. We did a few sensitive studies to change the composition of the injected gas, natural gas here, to look at which one gives better performance in terms of enhanced oil recovery. So here is some result here. This is increase the recovery factor. The base case is original water flooding recovery factor. Here, this is on the base of water flooding recovery factor, how much improvement. For example, if for this composition, right, we have better result, include 2.28 factor. So increase the recovery factor, only change the composition of inject gas, make a little bit of rich gas injection, not a lean gas, not pure CO2, pure CO2, not CO2, pure like methane here, right? The improvement not that big. Here to look at injection pressure. Higher injection pressure, we have better recovery because better miscible condition can be achieved. Then this look at injection, how long we inject. So this gives you some idea here, right? Inject 10 days, 50 days, or 70 days. Then it's eventually no much impact, right? After like 80 days, no much improve in terms of recovery factor. Then the last sensitive analysis is relative to soaking period. How long we soak? You see here the optimal here, about 10 days, like a week or 10 days, not very long. So this is give us some idea how to use numerical model to design huff-puff operation for natural gas huff-puff operation EOR for tidal reservoirs. Okay, now I'm going to conclude some conclusion and recommendation. We have worked very hard on developing some modeling tool to look at CO2 EOR and natural gas EOR for tidal oil reservoir EOR operations. Develop in-house model, several in-house models, isothermal, non-isothermal, consider geomechanical impact and also thermal impact. Again, I want to emphasize EOR, gas EOR is currently only viable approach used for tidal oil production in the US, because I work both the real reservoir in the US, tidal oil reservoir or EOR and also China. So currently we have like today maybe $41 per barrel of oil price. Gas EOR still okay now, still can be feasible. So for this particular study, we use gas injection for feasible study with gas EOR. We confirm rich gas has better performance to increase oil recovery factor. It's really impacted by many other factors. Composition, how to make the design the composition, the recipe for the injected gas, and also valve placement design. Again, the lean gas, dry gas, by methane alone is not really much improved for this particular application. So rich gas really get better performance. This is pretty much from the modeling study. And actually, I didn't report the lab studies. Okay, I would like to thank all the sponsors, Special Energy Simulation, CMGL, Chevron, and Rapid. So for the sponsor our research, and also thanks to all my graduate students and colleagues in my research group. Okay, thanks a lot.
Okay, thank you, Dr. Wu. There's a few questions I can combine, at least two. From geomechanics, using mean stress, you are probably taking away the shear stress and deflatoric effects of having the tensors. So the question is, how much physics do you think you're losing because of this?
Mean stress, we do. Actually, later on we publish some, we can calculate the even shear stress, but of course, based on assumption, it's really deformation is relative like expansion or shrinking, right? The rock, yeah. We can calculate the shear stress actually after we stop mean stress rigorously actually.
Okay. The questions were from Marcio Murad from LNCC in Brazil, and also Vijay Srivastava from CMG. Another question from Dr. Iraj Shaggy again. He's not clear as to what you mean by cold CO2 injection. By the time CO2 gets to 8,000, 9,000 feet, it is no longer cold. So could you elaborate on that?
Okay, good question. Yeah. Basically, we look at the inject temperature. It's not the same as reservoir temperature, right? Because the CO2 injection is huge injection rate actually normally. So you need once inject into the reservoir, we are calculated. Physically, it's mixture with reservoir fluid, right? Temperature will gradually increase to reservoir temperature, but not near the well. Near the well, it's controlled by inject temperature actually. The temperature controlled by inject fluid temperature. So that's why the whole thing in terms of thermal impact is transient. As long as you inject CO2 not a reservoir temperature, you will see the temperature impact in near injector. Near producer is different because in that case, near producer, you have lower temperature. It's due to gas, right? From supercritical become gas phase, right? You need thermal energy to do that, right? Then the temperature is lower. Geomechanical effects.
Yeah, suffice to say that I think temperature effects will be taken into account at least near the wellbore region.
Right.
Okay, so one question from Dao Yong, Tony Yang. Dr. Wu, thank you for your presentation. As for your model validation pertaining to phase behavior study, are the benchmark experimental data obtained with or without confined effects? What are the major factors to be considered for the confinement effect during phase behavior studies in tight formations?
Okay, yeah, another very excellent question. The key here, we call nanopore confinement. Basically, once you have 2-phase or 3-phase, capillary pressure very, very strong. Then in the phase behavior calculation, for the free energy calculation for each phase, you have to use the pressure, not oil pressure. Like a conventional composition model, use one pressure. Here for oil phase, you use oil pressure, gas use gas pressure, water use water pressure. This is different by capillary pressure. So that capillary pressure impact by the pore size, right? Then also pore size impacted by geomechanics. So that's carbon. So that's the part of the calculation need to consider. It's very big. The pressure difference between gas phase and oil phase, the liquid hydrocarbon and the gas hydrocarbon could be very large. That's why that's the impact for like bubble point pressure, all that, everything changed actually.
Okay, I suppose this question from Osama Jivali refers back to about CO2 injection. Is CO2 would become supercritical, is that correct? As you inject into the deeper, hotter reservoir, right?
Yeah, the most case, we hope so. Definitely we want to reach minimal miscible pressure, right?
Okay. Another question, actually a comment back from Marcio Murad about the mean stress, use of mean stress in your calculations. I guess he would like probably a little bit more discussion with you that you cannot really resolve back to not considering shear stresses. So I would appreciate your answering the question offline through the Q&A chat, okay?
Okay, I will do that. Maybe I point out some of the publication we have.
Okay. From Andrew Gupta, what is the range of for MMP, your estimate for tidal reservoirs?
I think the MMP, we don't actually explicitly use the input. It's part of EOS calculation actually. But I was thinking, yeah, if you have the reservoirs, like say 3,000 feet deep or more, very likely the reservoir pressure is under actually at critical, supercritical, reach MMP already. except near the producer.
Okay, so let me try one more question before we close. From Mark Zhong, Dr. Wu, thank you for your presentation. After fully coupling with geomechanical effects, do you expect the time step size of simulation would reduce since the problem involves more non-linear issue?
Okay, yeah, another good question. So far, because the formulation we use, not much impact. You know, the internal mean stress, that equation almost linear. And also that steady state equation, steady state, no time dependent in the geomechanical stress balance equation. So not much impact actually.
Okay, so once again, I think there's quite a bit of discussion about the use of mean stress and kind of accuracy that you may be losing in terms of the physics and that kind of thing. So please feel free to follow up with the answered and open questions within the Q&A. So this draws to the close of our day one or half day Summit 2020 for energy simulation. We'll be back with 7 more research chair presentations tomorrow, starting at 7 a.m. Mountain Day time, and same time, same place. So once again, appreciate your attending and look forward to seeing you again tomorrow.